All right, guys, let's start back on here. So I want to find A dot B, and I can do that by taking the magnitude of AX times BX, doing the magnitude of AY times BY. That's a way that I can find A dot B. So I can say that's equal to 2 times then that negative 1. I can do plus 3, which is AX, times 2, which is, 3, which is AY, times 2, which is BY. So this is the same thing as AX times BX, plus AY times BY. Okay, so if I do this, I would get a negative 2 plus 6. Ultimately, then my scalar product of A dot B is going to be 4. So that's us answering the first part of the first question. But then it also says, so we determine the scalar product, but then it says to find the angle between A and B. So I want you to go back and think about that cosine theta is equal to A dot B over the magnitude of A times the magnitude of B. So I had us write this down. If A dot B is equal to the magnitude of A times the magnitude of B cosine theta, I need to find theta, then I need to find the inverse cosine of A dot B, which we already found. We found that to be 4 over the magnitude of A times the magnitude of B. Okay, how do I find the magnitude of A? I can find the magnitude of A. If this is A, 2i plus 3j, I can find the magnitude of doing ax squared plus ay squared, square root it, I get A. So if I did 2 squared plus 3 squared, square root it, what? You get radical 13. I want to do the same thing for B. If I had a negative 1 squared plus 2 squared, I'm going to get radical 5. So then ultimately, A times B is just going to be radical 13 times radical 5 in the denominator here. So A times B, radical 13 times radical 5. So I want to take the inverse cosine of this. If you do that in your calculator, you should get theta to be 60.3 degrees. So there is 60.3 degrees of separation between vector A and vector B. Okay? Okay, so for Monday, I want you to try this one for me. So all we're doing is applying this situation with a scalar product to work. So it says a particle moving in the xy plane undergoes a displacement given by r as 2i roof plus 3j roof meters as a constant force F equals 5i roof plus 2 j roof newtons, and that acts on a particle. Calculate the work done by the force on this particle. Okay, all of the things that we've been talking about so far have been when work is with a constant force. What happens when work is done by varying forces? So we can only use work is equal to force times displacement times cosine theta if that force is constant. It will not work on a varying force. So if we think about varying forces, we have to assume that during a very small displacement, which we like to assume that most displacements are small enough that this will work. We assume that during a very small displacement, which we're going to call delta x. So in this graph, all I'm showing is that I'm applying a varying force and a certain amount of displacement. And I'm just going to show that, let's assume that delta x, which is just a small sliver of the amount of displacement within this applied varying force. And for that displacement, because this displacement is so small, I can say that in this one tiny little delta x, that really F is going to act like it's constant here. So for that one particular displacement, work is going to be equal to the force. So it's going to be equal to the force that's being applied times then its displacement delta x. So for all of the intervals, work is going to be equal to the sum of all of these forces in their in their displacements. So we've done this because ultimately we've set up a limit. And I know you talked about limits in calculus so far, at least we should have done that. All we're doing is saying that the amount of work that we're doing with a varied force, we're going to break up that displacement until it's super, super small, where force will look and act like that force is going to be constant. Because of that, we can think about using the exact same work equation. So in this one, if the size of the small displacements approach 0, then ultimately we're going to get a limit. So if these start to approach 0, what I have is that the number of the terms in the sum is going to increase, is going to increase without limit, but the value of the sum is going to approach a definite value equal to this area that's shaded here that we call work. So all I'm doing is integrating then. All of these that I'm adding up together is going to be equivalent to the amount of this shaded region that I'm about to calculate here. So doing the limit is the exact same thing as calculating the area under this curve, and that's how we can find the amount of work. So we're going to designate work as being taking the integral from the initial x to the final x, and it's going to be f sub x, so that applied force, dx. So it's going to be with respect to then that x-axis. So the work done is equal to the area under the curve between my initial x and then that final x, okay? So again, we're just using this as the limit because when x is equal to 0, this is what is going to become an integral. So I can make these as small as I can and get delta x to be so small that force is constant. If I add all of those up, it's going to be equal to the same thing as finding that area under that shaded region.